Okay, so what I'm going to talk about today is a technique, a sort of an advanced software engineering technique for modularization and for distributing extensible software. So for distributing software that can be expanded by third parties, and that is the technique called as known as plugins, which is something that you probably all have heard of. So can you tell me some popular programs out there or frameworks that you know that take plugins? Come on, don't be shy. Anyone? Yeah. Yes. IntelliJ, yeah, pretty much everything, even Chrome. Right. So pretty much every very popular piece of software out there ends up one way or another supporting plugins. Um, the reason for, so what are plugins? So plugins are third-party code that runs on your own deployment site. Right. So there's the concept of the framework writers, the framework developers. There's the end users, so whoever ends up using some package of that framework, and then there's the third-party developers that develop more features, additional features for the framework that is to be used by the end users. And these additional features have not been packaged as part of the core framework because for many reasons, maybe they want to keep the core simple. Maybe they want to actually to expand the development of this ecosystem to lots of people. There's all sorts of reasons for doing a plugin architecture, which is allowing third parties to hook up and do more things with your software. There are probably Vim plugins. I actually don't know. Google will tell you. So today I'm going to talk about the mechanics of doing a plugin architecture and what's involved. Some languages make it easier than others to do this technique. But it's possible to do plugins in pretty much all of the languages, even languages that are not very friendly to this, like C, for example, and C++. But it is also possible with a little bit more effort. But the modern languages, the ones that support reflection, inversion of control, and all that stuff, it's very simple to do plugins. And the dynamically typed languages is also very easy to do plugins because of the dynamic nature of the types. So all of these things get a little bit more tricky when you have static types. When you have static types, all of these things are a little bit more tricky, and that's why you need reflection to do this kind of type in the type safe manner. When you are in a dynamically typed language, then many of the problems go away naturally because it's very easy to just the final check of whether something exists or not is done at runtime. So as long as in the runtime you guarantee that there's something with that name in there, then the thing works, and you don't need that extra phase of compilation to make sure that things are kind of complete. So let me go to the slides, and I'm going to go through a deck of slides, and then I will move to show you code of an example of plugins. But so when we talk about modules in programming, we sometimes talk about many different things. As usual, we use the same words to denote lots of different things. So one way of using the word modules and modularity is at the conceptual level. So, when you're doing some sort of object-oriented design, for example, then you can call that the classes are some sort of conceptual modules, right? And in fact, there are software metrics to measure, the cohesion and coupling of these modules with each other. But so there's the conceptual modules as conceptual units comes in when you're thinking of doing some sort of a design work. But there's also modules as physical components, and that's sort of where the word really comes from. So, and in particular from computer engineering, and even before mechanical engineering. So there's there's the notion that we have these computer components, right? You have the motherboard, and the motherboard has some standardized interfaces with towards which you can apply certain modules, right? And these modules are sort of interchangeable, or you can have many modules that plug into the same interface, right? And so this kind of concept was, in fact, what made the computer industry bloom, right? Because the idea that you have a standardized interface, and then many vendors can make their own components towards that interface. It allows many vendors to sell competing products, right? And without that being very complicated for the end user, the end consumer, right? Because now the consumer can just buy whatever is cheaper or better or whatever, and it applies to the standard interface. This is a very powerful concept. Again, it comes from many centuries ago, but I think it's really kind of bloomed with computer industry, because this is where it became really important to allow for competing products to be on the same kind of interfaces without having to without that being super inconvenient for whoever's using this, the whole package. So there is the concept of modules as physical components, physically separatable components. So what does this mean in software? So this is a well-known concept in computer engineering, but in software engineering, you can also view modules as physical components. So modules are not just design ideas; they can also, and that they are also physical units, independently physical units. So they can be, for example, you have the source component, the files, right? So for example, the files are contiguous, chunks of disk space, right? Or at least for the purposes of our use, they're kind of, one file is different from another file, separate. It's just two different things, physical things. So you have a lot of binary components, like the jar files, the DLL files, the shared object files, and all sorts of other packaging techniques for other language ecosystems. And so, but for when you're trying to put these components together, once you have these jar files or DLL files or whatever, and you see them as physical modules, right? Independent modules. The idea is that then these kind of off-the-shelf components, you want to put them back together, right? That's the idea, coming from computer engineering. You want to do the same kind of stuff, right? But with the, if you want to do the same kind of stuff that you do in computer engineering, you want to do it in software engineering. If you have the source files, then that's no problem, right? You get the source, you copy it into your own project, you compile the whole thing, there's no problem. When you actually go in, but that's not really separate, right? There is a concept of the file is a separate thing, but then you produce the actual executables out of that, and that's a different story. It may do different divisions and the files themselves. But when you get the binary components, so the things that you actually are ready to run, right? That, and then putting those binary components together, that is a little bit more difficult, right? It's not so simple. It requires a little bit more work, let's put it this way, because again, we need to think about interfacing, right? You got some jar file or some shared object file from somewhere. You want to plug it into your code that you already have, how are you going to do that? Like, how do you know what kinds of things that module has, and how do you connect it to the interfaces that you have, or vice versa? So I'm going to focus primarily on linking binary components, and the reason for that is because this is what really matters out there, right? When you're doing a large software system, and you're trying to make some sort of a plugin architecture, meaning that you're trying to allow third parties to develop for your framework, right? What you really want is that all of these things are distributed in a binary form, because the end user, whoever is going to use the final package, you don't want for many reasons. One of the reasons is you don't want to force the end user to have to recompile everything again. Right? That's, recompiling code is a very big deal, and not everybody who uses, for example, IntelliJ is capable or willing to compile IntelliJ from source before using it, obviously. So you want to have IntelliJ, the framework distributed in binary form, is precompiled for people to use. And then you want those plugins, those third-party things, to also be distributed in binary form. And you want that to connect with the binary that the end user already has. So this is what you want. You want to be able to distribute binary components. You want to be able to kind of put them back together, okay, in binary form. So in order to do that, you basically have 3 steps. So the first step is that you have to ensure independent compilation. So what that means is that you compile your framework independent of any third-party plugin, okay? And maybe vice versa. Not vice versa is not so obvious, but you want the plugins also to compile so that they depend as little as possible of the entire code of the framework, right? So you want the plugins to compile only depending on the minimum amount. Basically, they just need to know the interface. That's all they need to know. How do I connect my code, my third-party code, to that big framework code? Then I just need to know the interface, not the entire thing. So in order to compile my plugin, I should not have to compile the framework, right? So that's another thing. So things should be independently compilable, so that you produce these different, modules without needing the entire source code of everything. So that's step number 1. The step number 2 is that once you have these binary components, the framework and the plugins, third-party plugins, the end user is running the framework, and you want somehow to be able to load those plugins, those third-party plugins dynamically, right? Because you don't, the user can install these plugins at any point. So you want to be able to install them, and you want to be able to load them dynamically. And finally, loading, and by loading, I mean literally, you want to be, loading means taking the executable files, or bytecodes or whatever, and loading them into memory, so that the virtual machine that runs the entire code can actually access the classes of the third-party code. That's what loading means. And then finally, after loading, then you want to be able to instantiate classes out of these plugins, of this third-party code. And again, when you write the framework, you don't know the names of those things, right? You just don't know the names of those things. That's something that is only known much later, actually in the user side. So this is where you need to use some reflection kind of techniques. So I'm going to go through these 3 steps. So and first, let me just tell you that when you have a dynamically typed language, all of this stuff is relatively simple to do. And a statically typed language is not so simple. Let me see if I have, I have an example of doing plugins in Python. Okay, plugins in Python is relatively easy because Python is a dynamically typed language. So if you look into the term frequency program that I have, for this chapter 20, this is what it looks like. So this is sort of the framework, right? The framework code is super simple. It actually doesn't have anything. It just has the most important function is load plugins, right? So the idea is that you have a generic framework that doesn't do anything, it just loads the plugins, and it just assumes that after loading the plugins, there will be a function called some package called tfwords on which there is a function called extract words. And there's another package called tfrex on which there is a function called top25. You know, I just decided to have two plugins rather than just one. Okay. So all it knows is that after loading the plugins, there will be these functions there, but these functions are not defined in the framework. So these functions are supposed to be provided by third parties. And so this is the framework code. And then we don't need to worry about types or anything. And if you look, then do I have my things here? Let me go to. I'll show you the plugins. Right. Okay, so there's this is the framework code over here that I just showed you. So basically the framework is totally generic. It just assumes that there will be these two functions, extract words and top25, that are given by two packages that are plugged in. And then the code of those packages, I have them here on purpose. I kind of divided on the source. So this would be the plugin source would be in somebody else's, you know, repo, right? It would be somewhere developed by somebody that they have the source. So this is, for example, two implementations of the frequencies package that has the top25. This is one implementation. This is another implementation. This would be, I just have everything on the same folder, but this would be, you know, two things developed by two different people. And here's the words, one implementation of extract words and another implementation of extract words, okay? So these sources would be in somebody else's repo, not here. And so what these people would distribute, in Python, you have the option to distribute the source code, but you also have the option to distribute a compiled version of source code. So in order to make this more like plugins, I have also a plugins direct folder here in which I have the compiled version. I don't know if you guys know, but you can pre-compile Python into a .pyc file, and this is the bytecodes for the file. Brooke, I will go to your question. Brooke has a question. What's the difference between the plugin and library? I will answer that question once I'm done explaining. Right. So you distribute typically the plugins in bytecode form or executable form. And again, there's many reasons for that. Reason number one, I already told you, is that you don't want the end user to have to compile anything. But the second reason is that in many of these architectures, in many of these systems, you actually don't want to distribute source code, right? Because the source code is proprietary. So you want to distribute just binary code. That's why you distribute binary code. So having these plugins in Python, this is relatively easy to do, because you just this is how you load. There are many ways of actually. I could have done it in many ways. So I'm loading the source. So the precompiled version of the words plugin, load module, and then I have this module. This is equivalent to the import statement. Okay, this is a programmatic version of the import statement in Python. You just to import lib, and then there's an API to programmatically import stuff. So once you do this, then the code relies on the hope, which is a hope that there will be a function called extract words in this module. If at runtime, if this function exists, great, it works. If this function doesn't exist, then it will be a runtime error, right? But that's the dynamic nature of Python. But it makes it easy to make these kinds of plugin architectures, because you don't need to check anything at compile time. But on the other hand, it's more risky because something may go wrong and this function is not there, and then things don't work. So there's no guarantees that this function will be there, basically. Now, and another thing that happens in plugin architectures typically is that there is a config file. Okay, some config file. There are many formats for config files. Maybe INI, which is the one that I use most. XML. There's a few others. And in this config file, or then this is where the end user decides to specify what plugins to use, right? So for example, in here, I'm saying that the words plugin is given by this file, words1 PyC. The other option would be words2 PyC, and the frequencies plugin is given by frequencies1, and the other option would be frequencies2. So in here, okay, externally to the code, without this is the only code that the end user writes, right? There's the framework that's written by the framework writer. There's the plugins that is written by the third-party developers. And the only thing that needs to happen at the end user site, at deployment site, is some sort of a configuration specifying what plugins you want to enable, what plugins you want to actually plug in. And that is done in a declarative manner, something like a configuration file of some sort, okay? So that's typically how these plugin architectures work. So as I said, in dynamically typed language, you don't need to worry about types during independent compilation, because there's, even if you have independent compilation, it doesn't really do the type checking of the static type languages. But when you go into a language that is statically typed, and that's why I wanted you to do this week, I want you to do the, statically typed languages. Things are a little more challenging and more interesting in many ways, because suppose this is Java, it could be C#, it doesn't matter. So you have an application, so you have the framework. Suppose that you have your framework, right? And this is the main function. And then you would say, load plugins or whatever, you end up with something top 25, you have some module that has some method and another module that has another method, but what are the types of these things, right? We have to declare the types of these things, which is something that we did not need to do in Python. In Python, you need to declare the types, but in a statically typed language, you need to declare these types. So let's see how we're going to solve this problem. So the first thing that we need to realize that we don't know the implementations of these functions, right? These are, in fact, there can be many implementations. There can be many classes or whatever that implement these methods. We cannot, as the framework writers, we cannot decide that this is certain classes with certain names, because we don't know what those classes are. This by the third party. So the best we can do is actually define the interface, right? We as framework writers are the ones that decide what kinds of interfaces we want out of these third-party plugins, right? So here's the interface for the TF words, and we're saying that there should be a method called the extract words with this signature, and here's the other interface, TF frequencies. There should be a map called top 25 with this signature. That's all we know about the third-party code. Okay, that's all we require. That's our contract with the third-party code. And now the types are okay, right? So the types, we can declare the TF words and TF freq to be of these types. Okay, so now we solve the type problem. So we solve the type problem by declaring interfaces, okay, at the framework level. Okay, we don't need the final classes, but we just need the interfaces. Now, but we still haven't solved the entire problem, because yes, we have the interfaces, but if we want to invoke something, we need to instantiate something. We need to create an object, right, of some class that we don't know. And so basically this part over here, what do we initialize these objects with? What is it that we instantiate? And I will tell you in a bit. Hang on to that piece of the puzzle. But before I even explain how to do that, keep in mind that there will be a way of doing that, and that's going to be, using reflection. Another thing that I want to talk is, even in this example, you can already see there'll be several ways of compiling these different things together. So some of these ways are the right way, and some of these ways are not the right way, and then there's some in the middle somewhere. So let me explain. So the whole model of what's going on is that you have a TF application framework. So this is a class. This is a class that relies on the existence of these two interfaces, right? It uses these two interfaces, and the plugins that are actually going to implement these interfaces are going to have classes that are going to implement these interfaces. So they need to know about these interfaces. They don't necessarily need to know about, actually, they don't need to know about this class, the TF application framework. All they need to know is about these interfaces. That's all they need, right? So now we can talk about how to partition the jars. I'm going to talk about jars. I'm going to use the word jars, but it could be DLLs in C#. It could be any other package in whatever language you decide to use, okay? It just happened that Java uses these things called jars, which are basically zip files, okay? With .class files inside. So the question is, how do we partition? Where do we draw? What do we compile together? Like, what compiles together with what? So one way that we could, do especially, if it's very simple like what we have right now, we could just say that this whole thing on the left is a module, right? And so we package the framework along with the interfaces. We put it in a jar file, call it pack1 or whatever. And then when we have, the third-party developers that are going to have to compile their own things, first of all, they depend on these interfaces. So because they depend on these interfaces, they're going to, when they compile, they need to have this jar file around. Otherwise, they will not compile because they don't know where to get the interface TF words or NTF frequencies. So this jar needs to be present at the site of the third-party developers, right? And you could even imagine that you have, one pack per class or not. So this would be one way of doing it. Another way of doing it, which you see in many frameworks out there, is separating the implementation. So you have a large project, and that large project is supposed to be a framework, and it has, plugins and whatnot, plugin architecture and so on. So typically, in order to make things easier for third-party developers, instead of packaging the entire framework in just one single package, you can have several packages, right? And one of the packages is, for example, just the interfaces. And that is the only package that you need to give out to third-party developers. You don't need to give out the code of the framework itself. You just need the interfaces. And so this pack2 over here, if you do this, will need to be present for compiling the framework, and it needs to be present for compiling the third-party code. But that's all. It's literally the interface. And that's the only thing that is shared among the two sides of the world. Let me show you. So another way of doing this, and this would make more sense in the case of this example, would be to package the words and the frequencies 1 in one package, and the words 2 and frequencies 2 in another. So basically, this would be done by one third-party developer, and the blue one would be done by another third-party developer, right? It would provide both implementations for both interfaces in this particular case, but it could be also separate. This would be okay too, and this would be okay too. This one, I want you to think about this packaging. So this packaging would be one that you would put the framework in one package, and then you would package the interfaces and the plugins in another package. And typically when I'm teaching live, I stop and I ask people, what's wrong with this? But you guys are all with your videos, so I don't know if you're listening. What's wrong with this? Does anybody want to tell me what's wrong with this?
So hadn't we created the interfaces to be able to use the words class, for instance? It's again gone into a package, so we don't have it anymore.
Yes, this doesn't make any sense, right? From a plugin perspective, because you're just packaging the interface that's supposed to be extended by third parties. You're packaging it on a third party. This doesn't make any sense, basically. Right? The interface is part of the framework, right? It's the framework developers who define the interfaces. Whether they package those interfaces with the framework code or they provide a smaller separate little package, that's a decision that they have to make, but it's part of the framework developer, definitely not part of the plugin development. So this is definitely wrong. This is the wrong packaging. Okay, but so having talked about these are all things that you need to consider in doing your homework, for example. So obviously I'm arguing that you should do something either like this or like this, okay? So, all right, so we looked into independent compilation. So independent compilation, we got it, right? So how do you compile these things independently? You have this layer of interfaces, okay? And that's the only layer that is shared between the framework and the third-party code. And once you have that, then you can compile them independently. You don't need the big framework to compile the plugins. You don't need the plugins to compile the framework, and you're done. Okay? You are able to compile these things separately. Now, once you have these three things separate, and you go into the deployment side, so the end user side, you have to be able. The end user is running a framework, right? And the framework needs to be able to load whatever plugins the user decides to use, and it has to do that in a dynamic manner because we don't know a priori which plugins are going to be used. So this is the part that comes back to these two lines that I left. And decided in a few slides ago. So what is in here? How do we load? Because we have to have classes here in order to instantiate objects, right? It's not enough to have interfaces. We need to have concrete classes. And we know that those classes are going to be in these third-party developer jars that are going to be available in the end user site. Right? We know that. So we will know what are the names of those jars, right? We know that as framework writers, and I'm very much focusing on the framework writers here because this is sort of an architectural decision, and this is where you start being a little bit more advanced is when you write these kinds of plugin architectures. So we as framework writers know that there will be in the user side, there will be a jar file or whatever, DLL file, a package of some sort. We know that we will know the names, right? And we know that those packages have been compiled for the interfaces. So we can rely that they implement certain interfaces that we have defined, right? We know that. That's all things that we know. So all we need to know is, so we cannot do this, right? We cannot say new words one, new fracs one, because that would be immediately tying our framework code with some particular implementation by a third party person. We cannot do that. So this doesn't work for plugins. This is not how you do plugins. You cannot refer to third party code in your own framework. So basically we want to do, say we have create an instance dynamically of something, right? And that something is given by name in some configuration file, right? That's what we want to do. So dynamic loading of libraries in Java can be done in many ways. Okay, there's many ways of doing it. There's basically the basic idea is a class loader class. There's a class in the Java JDK that's called the class loader, with which you can load classes dynamically. Okay, so you can load more classes. When you run the Java virtual machine, you say Java and then you say some file. typically when you do that, when you run Java and then some file, the virtual machine makes a check to make sure that whatever that file needs, whatever other classes that file needs are there in the whatever number of the class path, available in the class path, right? So you run Java with some class path, with some jar files or whatever, and then the Java virtual machine is going to make sure that it can find all of the classes that that the code refers to statically, right? Statically. So that's the normal use of Java. Now, this is an advanced use of Java where there's the concept of a class loader that at runtime, the program can load more classes. Okay, this is at runtime, so it's not. So these are classes that you don't know a priori what they're going to be. Their names can come. The files of the jars can come at runtime. Okay, you don't need to put them statically in the class path. It can be known only later on. And let me tell you, this is very widely used in mobile programming, for example. Mobile programming, it's if you want to shrink the size of your app, you can basically shrink the size of your app to be a very small thing, and then it's only when you run the app that you download stuff dynamically, right? And so all of that stuff you download dynamic, and then you have to load it dynamically. Basically, the rest of your program comes only when the user runs the application. Okay, so this is done with the concept of a class loader. In .NET, there's a similar thing. There's an assembly class that it does the same thing. It's possible to do it in C++ in Linux with DLOpen and raw C++. In Windows 32, there's also a load library function that you can use. I'm less familiar with this than I am with the languages that have virtual machines, but I know that it's possible to do it too. It's just more complicated in C++. So dynamic loading is with some sort of a class loader, assembly loader or something. Okay, so we need to know what packages are. This is where the user says, okay, I want to use this extra jar file, and it gives the jar file by name. Okay, and then you load that jar file into memory. And finally, once you have loaded those files into memory, then we want to create instances. You want to create objects that are instances of those classes that have been loaded dynamically. And that's where you use reflection. So you use typically the name of the class is also given declaratively in the configuration file. This is basically how you do it in Java or .NET or C++ again is a little bit more tricky because there's no reflection and stuff, but it's possible too. But it's a lot more hacky and not so obvious. So independent compilation, dynamic loading, and instantiation of classes. This is what you need to have plugins. So now let me go here to my REPL, and I want to show you how to do this in Java. And I want to show you, and I know some of you are going to do this in Java, but I just want to show you because this is a homework that typically a lot of students have some doubts about how to do this because it is advanced stuff. So here's what I have. So ignore the main because this is the reflection code that I was showing on Tuesday. For the plugins, I have these 3 folders. I have the framework folder, okay, that has the framework code. I have the app, which is the plugin, okay, the third-party code. It's supposed to be the third-party code. And then I have the deployment site. Okay, this is the end user where things are going to be put together. The framework and the app are going to be smushed together. So the framework has, this is not term frequency. This is, what is it that I'm doing to do? I say, enter the name of a class to use, and basically loading, instantiating this. All right. I actually, this is the part that should be in the configuration file, but I just have it hard coded in my code. This is typically should be in a configuration file, but this is the string that basically comes from the outside and saying which plugin, which jar file do I want to connect to my code. All right. And so I just have hard coded here. And this is going to load that plugin. And then here, this is actually going to load that plugin over here. And finally have the class, load the class by name, right? The class that I want to use. And then I create an instance of that class and then I call it. And this is the application. So so basically what I'm doing here is it's a completely generic code that calls some operation, okay? Some addition or multiplication, okay? Or division, it could be division. So I have the notion of a surprise operation, okay? This is what's the most important thing. I have an interface called surprise operation of two operands, integers, okay? A and B. And this can be implemented in many ways. And so basically what the framework does is that it loads some concrete implementation of a surprise operation and it calls it. All right, that's all it does. So in here, in the app, I have two implementations. This actually could be two different apps, right? So one is an addition and they implement surprise, and one is multiplication. It also implements surprise, okay, and it does multiplication. So this is the code, and then in the deployment site, you want to put one with the other, and this is where you actually want to run things. So how are we going to do? What's the concrete steps to do what I just explained? This independent compilation, dynamic class loading, and then the reflective instantiation. So first thing that I'm going to do here is to compile the framework. So the framework needs to be compiled. So I go here. Let me just show you what's in here. I already had a framework.java here from last time that I taught this class, but basically what I'm going to do here, the only thing that should be here really is the iSurprise and the framework.java. You know what? I wish I could delete this. Can I delete from here? Delete. And remove star.class. All right. Now we're rolling. I have a manifest too. I'll explain a little bit more what this manifest is. So, but with respect to Java, I have only these two files, framework.java and the surprise.java. So now I'm going to compile them. And I put my script here because I don't remember these steps. So Java C star.java. Okay, so now I have this creates the class files, right? And now what I'm going to do, I'm going to package them. So for those who don't know how to create jar files, there's a jar command in the JDK that you can use. The jar command is almost identical to the zip command. It's actually it's some sort of a wrapper on top around zip that packages things, just creates the package. So what I'm going to do is I'm going to create this framework.jar file that has all the dot classes. Okay, and I'm also going to put a manifest file. So let me show you what the manifest file is, because this is something that it's very Java centric. Okay, I'm just going to explain to you. This is something that you need to put in the jar file when you want to be able to run that jar file with a default main method. Okay, if you want to just say Java and then you give just the name of the jar file and you don't want to specify anything else, then what the VM is going to do is going to look into a manifest file inside that jar file and check what is the main class. Okay, So in this case, it's called main. Is it called main? Yeah, it's actually called main. Okay, I'm sorry. I should have called it framework. So the main class is in the file called framework.java, but the class itself is called main. And the manifest is saying that the main class is actually called main. This is where you find the main method. Okay. So having said that, I'm going to create the jar file like this. Copy. All right, so now I have this framework.jar. Okay, and this has been compiled independent of any plugins. Okay, there's no plugins in here. There's just these two files. So now I'm going to the application. So the third-party developer has these two implementations as plugins, and they need to also package that, right? So in order to package that, they need to have access to the iSurprise class, right? Because this addition and the multiplication files implement iSurprise, this interface. So in order to be able to find this, you have to be able to have access to this jar file that I just created. Okay, in this case, I put both the framework and the interfaces in the same jar file. I could have done it differently, but I just created just one package because this is so small. So now what I'm going to do to compile this separately, I'm going to go to the app folder. And what's in here, we should remove all the class files. And I should remove that app.jar that's been there since last time. So now I have just the source code. And I'm going to compile the source code. And now look how I'm going to compile the source code. I'm going to compile the source code by giving it the class path to the framework.jar. Otherwise, if I don't do that, if I just try to compile this without giving it that jar file, this is going to complain that it doesn't know where to find the iSurprise. Come on, see, so it doesn't know how to find the iSurprise symbol. So I have to give it a path to the jar where it has that definition. So the third-party code needs to have access to the interfaces. But in this particular case, it also has access to the main class, but it doesn't use it. But it could, it could, but it doesn't use it. But the interfaces are the ones that you need to have access to. So now I compiled, and now I'm also going to package this separately. So these are my plugins, right? So I'm going to compile this. I'm sorry. Create a jar file called app.jar. And in this case, I don't have any manifest file because this is just a plugin. The plugin does not have the main method. So I will never run this independently. So that's why I don't even have a manifest file in here. Okay, so now I have my app.jar in here. It's compiled and I have it packaged. So now I would go to the third part, the end user site, right? So now I go to the deploy site. This is where I'm going to remove everything in here because I've been here from before. So this would be the deploy site, the end user site. And what's going to happen here is where the assembly takes place. Right? So the framework and the app, this is where they come together. So what I'm going to do, somehow you download or whatever, you'd have to get these two jar files, right? So let me just copy them here. At the end user, all you have is these two jar files. Okay, you don't have the source code, you have these two jar files. And beautifully, I don't have to compile anything. That's the important thing. As the end user in the final deployment side, I should not have to do any assembly whatsoever anymore. I just need to run the framework. Okay? That's what the plugin really means. So how do I run the framework? I do this, Java. Okay, I'm not compiling anything. I'm just running the framework.jar. Okay, and this one has the manifest inside that tells it what's where the main method is. So now it's running the actual framework. So it's asking me the class name to use, let's say, addition. All right, so there you go. 10. And then I say multiplication. All right, there you go. Okay, so now it's doing the framework code, which is doing, now you understand what it's doing. So it's asking the name, and next it's downloading. This runs in the framework.jar, right? So the framework.jar is going to dynamically download the app.jar that I have there, right? In here. Okay, and dynamically loads that app, that's a jar. And now you have, what you can do now is that you have a bunch of class URLs that come from that jar file. Okay, and you associate a class loader for those URLs that came from that jar file. And so that once you have that class loader, then you say, okay, load a class with a certain name. Okay, and from those names that you got from that jar file. And now this gives you instantiates a class in memory. Okay, dynamically. And once you have that class, then you can create an object of that class, an instance of that class, using reflection, using the new instance. This is reflection. And then you can call it. All right. So I want to just go one more time to this line 26 here, because this is something that perhaps not many of you are aware of how these languages work. And this is true for Java, it's true for C#, it's true for a lot of these statically typed modern languages that have a VM of some sort. So if I just, if I have, some file here, whatever, I have a main here. I have a main. So whenever I say Java and then I say some class or some jar file, what the JVM is going to do is going to traverse the graph of dependencies to make sure that whatever the main class depends on is actually available on the class path. Okay, so this, as you know, there's the class path in Java is the place where you find where the Java virtual machine tries to find bytecodes, right? So this is there's a set of statically already existing classes that are placed in whatever the class path is pointing to. Okay, and that is where the Java the JVM is going to look up when there's a reference of a class. Okay, and it's going to load that class up into memory, right? So what's happening in this other code is that I'm expanding at runtime the sites on which the JVM is going to look up for bytecodes, okay, for dot classes. And that is not just the class path, which is sort of the default place where the JVM looks for classes. But now I'm telling you, hey, there's this other place, okay, this other jar file where you can also look for classes. Right, and now I'm saying that in particular load that particular class out of those in this new site that I just told you. Load the class with a certain name, and this is when now the bytecodes that are in that zip file are going to be loaded into memory. Okay, this is a dynamic thing. It's dynamic. It's at runtime, and it's by us, the programmer. We can do this. We can tell the Java virtual machine to load more things at runtime, more code at runtime. Okay, and then once we have that class, then we create. We don't, we created the instance with using reflection. All right, is that sort of clear? In whatever other language that you decide to use, if it's statically typed and it has a VM, very likely it's going to be very similar. They all have different names for these things, but the process is very similar. Questions?
Professor, I had one quick question. You had copied the app. You had mentioned about this actually, about hard coding the URL for the app.jar, but you'd also I mean, I'm not sure. So you copied the app.jar to the deploy site, but I don't know if that is being used at all. So is that being used or?
I did deploy it. I did copy it to the deploy site. It's
Yeah,
there.
yeah, but so you, I mean, okay, so the kind of the copying part of it is just representative of the fact that this is being done at the deploy site, right? That's
Right,
why.
exactly. Right. So, so in reality, when you use jar files and use this kind of thing, this can actually be a URL. It doesn't need to be in the file system. It could be from some
Right.
server somewhere. Yes.
Okay.
Yeah. And let me tell you a little secret that I already I mentioned. I hinted that mobile applications, and particularly in the Android world, okay, that uses some version of Java. Is it Kotlin? What is the version of Java that it's just Java, right? That Android uses.
Yeah.
Yeah. So many apps do these dynamic loadings of new jars for many reasons. Okay. One reason is to shrink the size of the app that the people install. Okay. So in installing, you install a much smaller amount of code than if, but then when you run, you dynamically load more code. That's one reason to decrease the size. Another reason is to well, put malicious code on people's computers to evade the checks that the App Store does on third-party code. So, the Android App Store scans the applications for malicious code, right? If if the code that you publish is not complete and you're going to load dynamically, then that code, dynamic code that is loaded, it completely bypasses, it is never seen by the App Store. So a lot of malicious code in the Android ecosystem is deployed with this kind of technique. Right? It's a hard thing to catch. But as usual, with these powerful techniques are super powerful, and they can be used for many good reasons, and they can also be used for bad reasons. And just so there's a good, can the Android store also scan the URL code? Then they would have to do a deeper scanning, looking for things like this, right? So they would have to look for the use of these particular APIs, and then load them up, which would perhaps open them up to another can of worms if they would, maybe that's on that endpoint is not what they would expect. Yeah, it's a difficult problem to track. Very difficult problem. I don't know the state of malware detection right now in the Android ecosystem. We have a professor here who's an expert in that, but I know from him and listening to his talks that the use of reflection is one of the big kind of open doors for malicious code. But as I said, it's this is absolutely important and critical to empower people to do plugin development, right? And plugin architectures. And plugin architectures are perhaps some of the most important architectures in software engineering, I would say. And I'm not exaggerating, because it really allows the development to be open to add lots of other, your team suddenly becomes the entire world, right? You can have this ecosystem. In fact, the entire things like the Chrome browser, the Chrome browser, right? So lots of plugins that other people have done and are continue to do for the Chrome browser enhance the ecosystem of the Chrome browser. It gives it more value, right? So these plugin architectures are really, really important, and so it's important that you all know how to do a plugin architecture, because it's super valuable. And this is independent of the fact that it opens up a can of worms that can be used for bad, but you should know that too. Okay, so the exercise, the second exercise of this week is to do this for term frequency in whatever language you want, but stick to a statically typed language because they are more interesting, okay? The dynamic ones are just too easy.